Welcome to Thermodynamics and Equilibrium, our second lecture, where we're going to introduce enthalpy and entropy. So just to remind you, last time, in our last lecture, we introduced the first law of thermodynamics. You will know what an isolated system is, a closed system, an open system, and you'll also know about transformations of energy between, say, potential and kinetic energy, and the relationship between this and the first law of thermodynamics, in that energy cannot be created or destroyed, but can be transformed. The objectives of this lecture is to introduce you to the terms enthalpy, entropy, and Gibbs free energy, and to describe the relationship between these three terms to each other. So first of all, let's look at this closed system. So a closed system can exchange its energy with the environment, but only its energy. It can't exchange matter, if you remember from last week. So we can see this exchange as either heat or as work. So heat is given the symbol Q. So this is the heat or cooling of the surroundings, and work is given the symbol W. So the change in total internal energy will be as a result of the movement of heat or the movement due to work. And although this looks like a different equation to the one that we were talking about last week, in the last lecture, where I was focusing on kinetic and potential energy, remember that every type of energy that we talk about can be talked about in terms of kinetic and potential energy, and both heat and work can be as well. So the total internal energy, the change in the total internal energy, not the actual absolute value, will be equal to the heat, so how heat has changed, and the heat movement, or work done. Now we're going to look at those two terms and explain those two terms in more detail. So first of all, heat. So heat isn't temperature. Heat is the flow of energy due to a difference in temperature between two bodies. We know that a system will always move to thermal equilibrium. So heat will always flow from areas of warmth to cooler areas. So if you have your glass of water with ice in it, you know that the ice will melt over time and the water that was originally very cool will warm. And your tea, you know you need to drink that fairly quickly, otherwise it will cool down. So this is because the systems will move spontaneously to thermal equilibrium. That's also known, by the way, as the zeroth law of thermodynamics. So this means that heat will always flow from areas of warmth to cooler areas until the temperature of both the bodies are the same. Work is usually mechanical, in that it is the transfer of energy causing motion against an opposing force, which you can see illustrated here with hands pushing, an opposing force pushing on a spring. So if there is a pressure change that pushes atoms in the same direction, then this is work. So our chemical reaction will have energy moving through it, through change in work or through heat flow. So this leads us to introducing enthalpy. if the pressure is fixed, as it would be in most reactions, we have an open flask, for instance, then work would result in an increase in volume. So if instead of a pressure change, that would lead to an increase in volume. And this is work being done by the system on the environment because it's pushing material out. Under these conditions, we can define work for cases where pressure is fixed and the volume changes as minus P delta V. So the pressure is constant and the work is seen as a change in the volume. This definition of work will be true for most chemical reactions. So in most cases in chemistry, we are working under conditions of fixed pressure, which is why we can say that this will be the case for most chemical reactions. And we can consider work done as expansion work, expanding into the environment. And so this is why we have that negative sign. It's W equals minus P delta V. So W is negative by convention. This means the change in total internal energy can now be written differently. So I said that the change in total internal energy was Q plus W. Well, now we have defined W as minus P delta V. So the change in total internal energy is now equal to Q minus P delta V. And this is where the change in enthalpy comes in. The change in enthalpy is defined as being equal to Q under conditions of fixed pressure, which is the conditions that we're talking about in this system here. So now the heat flow, Q, is delta H. So now we can change our equation further to delta U, so the change in total internal energy is equal to delta H, okay, the change in enthalpy, which is our Q term, minus P delta V, which is our work term. And this is true for most chemical systems. So enthalpy is the heat energy absorbed by a system at constant pressure. As you know, we usually consider enthalpy as the change in enthalpy. So delta H, change in H. We do not measure the absolute value of energy. But to define enthalpy through the rearrangement of the previous equation, delta H, delta U minus P delta V. But considering absolute values rather than changes in energy, then we could also write this as H equals U plus PV. So if we're talking about the change in enthalpy, we would then add our deltas in. Now it would become delta H equals delta U plus P delta V. So basically it's a rearrangement of the equation on the previous slide. And so that is the way to define enthalpy, and the way you may see it defined in textbooks. And it's a measure of the total energy of the system, and it includes these two terms, the internal energy term and the work PV term. Enthalpy is the heat energy absorbed by a system at constant pressure. So in the simpler terms, that is how I would advise you to remember enthalpy. And it is equal to Q. These diagrams might further help you to remember the important aspects of changes in enthalpy, delta H. If heat flows into a system from the surroundings, then this will lead to a positive enthalpy change, and it is an endothermic process. Okay, so the change in enthalpy will be greater than 0, and it's an endothermic process. If heat flows out of a system, so in other words, if the reaction creates heat, then heat is going into the surroundings from the system, then we have a negative change in enthalpy, and the process is exothermic. So delta H, change in enthalpy, will be less than 0, and the surroundings will get warmer. So we know from enthalpy that a reaction will either be endothermic or exothermic. Now, if it's endothermic, the process needs to take heat from its surroundings. Will a reaction like that occur spontaneously? We want to be able to predict if a chemical reaction will occur or not. Will a medicine degrade? Will the reaction occur spontaneously? Now, if it's an endothermic process, you might think not, but there is other things to consider. In fact, there's entropy to consider. As well as heat, there is also this thermodynamic process that we relate to order or disorder of a system. Think about a room where nobody puts in energy to keep it clean or tidy. It will eventually get messy. And it doesn't matter how tidy a person you are, if you don't do anything to work to keep it clean or tidy, it will eventually get messy. The natural process will be to create disorder. Entropy. Entropy is a measure of the disorder of a system. Solids have atomic structures that are fairly ordered, and gases, we know, have randomly arranged atoms. So solids have a lower entropy than gases. Entropy of isolated systems always increases. Think of this from the point of view of the universe, a chemical reaction. If you drop a box of matches, what happens to the matches? The natural world favors disorder and high entropy. The second law of thermodynamics is that entropy of an isolated system increases during a spontaneous change. Remember that we have a system and its surroundings, so the entropy of the system can be lower during a process, but the entropy of the system and the surroundings would not. Thinking about enthalpy and entropy, a process now can occur spontaneously if there is an increase in entropy of the system, so we increase disorder, therefore we increase the entropy, so delta S, change in S, increases. And this means the process could occur even if the enthalpy is endothermic. This example of increasing the temperature and going from a solid to a liquid shows that there is a relationship between entropy and temperature. Movement of molecules caused by heating increases disorder. So entropy is related to temperature. As T increases, so does entropy. This means that the entropy of a process will be different at different temperatures. It also means that it is possible to think of a very cold state where there is not enough heat in a system to allow motion. And under such conditions, wouldn't the system be completely ordered? Would a change in entropy become 0? The third law of thermodynamics says that a temperature of 0 Kelvin, so at that temperature, then the change in entropy is 0. Remember, change in entropy of both the system and the surroundings, the universe, is always positive, but the system may not on its own have a favourable entropy change. For a process to be spontaneous, the entropy of the system needs to increase, so delta S needs to be positive, or we need the process to be exothermic and giving out heat, which will lead to an increase in entropy of the surroundings. These now define the processes where we will have a spontaneous reaction. And so these are highlighted on this slide. This is a nice example. This is erythritol, which is a sugar alcohol excipient. Now, excipient means an additive, something that is added as well as the active ingredient. And it's used in mouthwash. The change in enthalpy during dissolution of this excipient is positive. So it takes in heat from the mouth, and this gives the cooling effect. And this gives the fresh feeling in the mouth. The process of dissolution also creates more disorder of the molecules that are dissolving, and thus increases entropy. So the change in entropy is positive, and this is why the process is spontaneous. So although it wouldn't be spontaneous only from the point of view of enthalpy, the change in entropy allows the process to be spontaneous. We know that we can now understand if a process within a system is spontaneous, looking at changes in enthalpy and entropy. So this means we can introduce Gibbs free energy and define it by this equation. Delta G, so change in Gibbs free energy, equals delta H, change in enthalpy, minus T delta S. So the temperature and the change in entropy linked together because of that link between temperature and entropy that we spoke of earlier. So for a process to be spontaneous, delta G must be negative. So that's the thing to remember here. For a reaction to occur, that means that either delta H, change in enthalpy, is more negative than an unfavourable change in entropy, or T delta S, so temperature multiply the change in entropy, but with a negative sign there, okay, is more negative than an endothermic delta H. In those cases, then delta G would be negative and the reaction could occur spontaneously. Consider the process of going from ice to water or even water to steam. Disorder of a material depends on temperature. And as we know, this would be an entropically favourable process. But we know that ice doesn't melt until it reaches 0 degrees Celsius. The melting process is endothermic in that it takes heat from the environment. Delta H is positive. At low temperature, the positive change in enthalpy is larger than the negative contribution that we get from minus T delta S. Delta H is greater than T delta S. And so delta G is positive and the ice doesn't melt. But as the temperature increases, we get to a point which we know to be 0 degrees Celsius, while delta H is less than T delta S. The temperature is increased enough. And so delta G becomes negative and the process will occur spontaneously. The ice will melt and the water, or if we were going from water to steam, the water would boil. When a process is spontaneous, delta G is negative. The equation shows that a spontaneous process also depends on temperature because we know that disorder of material changes with temperature. So this equation is very important in showing us that if something is spontaneous depends on the overall contributions of the enthalpy of the system, the change in enthalpy of the system, and the change in entropy of the system. For an endothermic process, delta G will be positive if we have low temperatures. So in cases where delta H is greater than T delta S. When the temperature rises, as we've seen with the examples that we've looked at, then the T delta S component will become greater. And at this point, delta G will become more negative and the process will become spontaneous. For an exothermic process, of course, you could get a situation where the two components both lead to a system being spontaneous, or the two components both lead to a system a reaction not occurring at all. Now, do remember that in all of these examples now, we do not deal with the absolute values of G, H, and S, Gibbs free energy, enthalpy, and entropy. We work with changes in. So you'll always see the triangle, the capital delta to mean change in. And that's a change that accompanies a transformation, a process that we are interested in. So that's the end of this second presentation. And so the third lecture is also ready for you to look at when you are ready.